few comments. So most of this work was done before I joined Argonne. So I should say that the results and discussions I would be doing today reflect my personal opinion and does not reflect the Argonne policy or recommendations. And before we talk to science, let me acknowledge all the wonderful researchers I have had the pleasure to work with, starting with my PhD advisors group, Partha Mukherjee's group at Purdue. Um, then got to work with Candler Smith groups at National Renewable Energy Laboratory. I also had the honor of working with Scott Roberts at Sandia National Labs. And Scott will be speaking tomorrow. He'll be showing some of his work. Then I got to work with a bunch of researchers at Argonne National Lab, which is my current home now, on different projects. I also got to work with a few folks at US Naval Research Lab and quite a few academicians like John Nelson from University of Alabama, Paul Sharing from University College London, Samuel Cooper from Imperial College London, and Sam, if I'm not mistaken, Sam will be speaking on Wednesday. Now, most of the work I'll show today is related to the first two groups of people that I work with, and parts of it were funded by US Department of Energy, few fellowship funds from Electrochemical Society, MRS, and Purdue University. With that, let me start the science part of it. So we are talking about porous electrodes, and if you sort of look under the hood, a battery analog of looking under the engine for vehicles, you would see porous structures like this, where you would have active materials, which are the red particles here, which essentially store lithium, and they are the energy storing phase. Now, we also need other things. We need electrolyte, which transports lithium ions from one electrode to another electrode. And on top of it, we also add things like carbon and binder for several reasons that I'll be talking as we move forward. Now, if you look at this entire problem, as it turns out, there are two different things. There are material properties of these different constituent phases that would reflect to the response. And there are geometrical arrangements that also contribute to the response. Now, a typical voltage versus, so as you keep storing lithium in one of these materials, a typical voltage profile would look something like that. But the blue curve shows the thermodynamic limit, which is essentially the theoretical limit. Now, that's purely a material property, and that depends on how much active material we have. Now, when we run these battery electrodes at some finite rates, right? So if you try to charge your iPhone in 2 hours, or if you want to charge your electric vehicle batteries, then what you would end up getting is something like the black line. The voltage response would be different than what you have thermodynamically. And essentially, the gap between the two reflects the losses. And those losses, in turn, are a combination of the materials that you use, and it would then entail the transport properties of these materials and the specific geometrical arrangement that you have. So one can go forward and sort of ask a design question that, okay, if I'm given a material, then it should be just a matter of finding some geometrical arrangement that will give rise to good performance. And if that's possible, and that is possible, right? We change the geometrical arrangement and the performance changes, then we should be able to design it. In other words, we should be able to optimize it for best performance. And we should be able to get to a base microstructure that will give a good battery out of it. Now, when we pose it like that, there are sort of two sub-questions that we haven't yet thought too much about. First is that what do we mean by the best performance? Does it mean that I want to get more capacity? Does it mean that I want to get a higher voltage? And there are so many other things that you want to get out of these batteries. And second thing is, there are inherent variabilities in these materials, in these porous structures, that sort of limit the precise definition of design. So now we have to think of design with these variabilities, right? So that's the key question I'll be addressing as we move through my talk. And the way I have done is I've sort of divided into three sections. I would first talk about the simple porous electrodes, sort of to set the ground for what we are talking about, which would only contain the active material and electrolyte. Then we'll jump into the porous composite electrodes, which would have the additional phase, which are this carbon and binder materials. And then thirdly, we'll talk about what if this electrode now is inhomogeneous. And I think it would be better if I stop after each of the sections, and then we have a few minutes of discussion. That way we have a bit more interactive process. With that, let me get to the first part of it, which is, let's first look at the simple porous electrodes. So situation would something like that, where the black line is one of your electrodes, and what you want to design is the other electrode, which is gray, and it will be sort of separated by electrolyte. Now what would happen is you would be diffusing lithium ions in between the two electrodes, and the corresponding diffusion length would be the thickness of the electrolyte. Equivalently, now what would happen at the interface of electrolyte and electrode is the reaction will happen. It will convert these lithium ions into lithiums, and this lithium would then subsequently get stored in the electrodes. Now it would have its own diffusion coefficient, and it would have its own characteristic length. And sort of the two diffusion coefficients I have mentioned are the typical values we see with the materials we have. We see that the electrolyte diffusion is fundamentally faster, about 4 orders of magnitude faster than the diffusion of lithium in the active material phase. And which sort of seems intuitive because you would expect a solid state diffusion to be slower. Now what one can do after this is we can define some time constants, which is essentially nothing but the lengths of this divided by respective diffusion coefficients. As it turns out, a representative time scale for lithium to diffuse in the active material would be about 70 hours if we start with this configuration. And correspondingly, the time scale for electrolyte diffusion, Li plus diffusion in electrolyte would come out to be 4 seconds. Now, we can plot it on a sort of this plot, and I'll keep referring to this plot as we bring on adding more and more complexities to these electrodes. Is you're fundamentally now limited. So what would have is you will have multiple time scales, and you will always be limited by the one that is the slowest, right? Think of someone like a person who is driving slowly on a fast lane. Now it will pile up the entire traffic and will be limited by the slowest driver. So it's the slowest time constant, or that means the largest time constant that we need to worry about. So on this plot, the time constant for lithium diffusion turns out to be much higher. Now, one may look at it and say like, oh, that's wonderful. That means I can use my phone battery for 70 hours. That may be true, but now what you would also have with that is it would take about 70 hours to charge it. So it's not a feasible situation. So the reason this film electrodes would be limited is purely because the solid state diffusion is so sluggish. Now let's do something else. So if the issue was the diffusion length in the solid, how about I break down the film electrode and make it into spheres? Now suddenly my diffusion length for lithium decrease, and it just have to diffuse to these small particles. And correspondingly, the time constant would decrease. It comes out about 0.7 hours, which is fantastic, right? Penalty that we pay is that now the lithium ions, which were just moving across a 20 micron length, would now have to travel a much larger distance if they want to meet the particles which are towards the other end of the electrode. So it's just that geometrical length changes. On top of it, what happens is, now it's not a clear medium. It has to go through these different crevices between the particles, which would introduce additional factors, constriction factors, which we represent by epsilon, which is the porosity, which is nothing but the volume of the electrolyte, volume fraction of the electrolyte phase, and tortuosity, which is nothing but the longer path it has to take to reach to the internal particles. And it increases now the time constant for electrolyte diffusion. So if you put it now on the time constant plot on the left, that is how things would look like. When we go for a porous electrode, we are making a conscious choice that since the most sluggish part was the lithium diffusion in solid phase, we are trying to decrease that time constant. Now, the penalty we get for that is that we are now increasing the time constant for electrolyte to pass, lithium ions to pass through electrolyte. Another conscious choice we are making with this is, if you compare with the previous one version, where the entire electrode volume was filled with the particle that can store lithium, that means it can store more lithium as compared to this configuration, right? So we just compare the theoretical capacity energy of the previous configuration, which is the film electrode and a porous electrode, you're bound to get a lower energy, lower theoretical energy. The advantage that you get out of this is that you are improving the transport. Now you will get a much better practical performance. You will be able to charge the cells in an hour, right? Unlike the 70-hour limit that we had previously. Now, this particular way of thinking in terms of time constant, helps us easily identify what are the next generation challenges for porous electrodes, right? And what I've done is I've added another axis at the bottom, which is essentially the reciprocal of this time constants, right? So when I want to, so if someone who is more familiar with the battery says that I'm doing a C/10 charge, it means that it's roughly going to take them 10 hours to charge these electrodes, the cells, right? Equivalently, if someone says I'm doing a 10C charge, that means that it's going to take them 6 minutes to charge it. Equivalently, if you do a 10C discharge, it's going to empty your cell in 6 minutes. So historically, first lithium-ion batteries were introduced in electronics, and that right now is about 10 to 12 hours of discharge life, right? That's your battery capacity you are looking at, which means that you are in about C/10 range, and which would mean that you are now limited by only the solid state diffusion. Your electrolyte diffusion limit is much farther. Second thing we look at are electric vehicles. We roughly want, if we are in US, we want about couple hundred miles of range, and that boils down to about 6 to 8 hours of discharge life, discharge time. And that would also give a little bit higher C rate, little bit higher current, but still similar time constants, right? Now, let's talk about one of the recent technologies, which is extreme fast charging. So now the goal is that these vehicles are going to, we want to drive them for 6 to 8 hours, but we want to quickly recharge them, and we want to compete with the time it takes us to refuel a gasoline tank, right? And that sort of gets us back to 6 to 10C range, where we want to charge them pretty fast. Other applications which are emerging right now are electric fight, which would also increase the current at which you are discharging, current at which you are charging. Electric racing, which will substantially increase the current you are discharging for certain spots in the lab. Another opportunity is low temperature. So trying to start these batteries at lower temperature without any external device. And what ends up happening is your diffusions become sluggish for both the phases, electrode and electrolyte, as you go to lower temperatures. And it increases your time constants, and that's why you get to now worse than before. Another opportunity is thick electrodes, which now increases the thickness of the electrode, which will substantially increase the electrolyte timescale. And the common denominator for most of this is that you're limited by electrolyte transport, right? In addition to being limited by solid state transport, which is the fundamental situation. Now, say how one of the ways we sort of try to increase the energy density of these batteries is increasing the packing. And what we are looking at is we want to put more and more active material, because that's the phase that actually stores energy, and you want to reduce everything else. And if you do sort of back of the envelope calculation, you get these lines where your active area increases with more and more amount of active material you put in. Now, if you're putting in active material, you are simultaneously decreasing the amount of pores that is available. So you're simultaneously decreasing the volume of electrolyte. That's why the top axis goes in the opposite direction. And at any point, both of them sum up to 100%. Now, what would happen is, as you go to higher and higher active packing, you would be limited by transport, because you are now going into very low values of epsilon over tau. And recall that epsilon over tau, that constriction factor comes in the denominator, so it will substantially increase the time scale you need to spend for lithium ion transport. And then it would make your electrodes more transport limited. Now, this is not the end of our troubles, because what we are missing here is that there's a limit on how much spherical particles we can pack in, right? The typical limit is about 55 to 65% for random packing, which would mean that we are sort of cut off somewhere in the middle of this plot. Now, someone may pose that, oh, we can sort of get by that by having a bimodal distribution or having a smaller size particles. The issue with that is you would now start seeing this crowding effects, where your electron transport becomes sluggish and the small particles which are sort of caught up between large particles wouldn't intercalate as easily. So all these things would further put limits on these issues, and you would gradually more and more become transport limited. Let's talk about the composite electrode part of it, right? One thing I haven't told you about is that this simple configuration has limitations. First is, how are you going to ensure the mechanical rigidity? So to ensure mechanical rigidity, you would need to put in something like polymeric phase, which is typically traditionally called binder. Another issue is most of the electrode materials, especially on the positive electrode side, are poor conductors of electrons. And when these intercalation reactions take place at the interface of electrolyte, which is the white phase, and the active material, which is the gray phase, they need electrons. And that electrons sort of are often supplied through the adjoining phase, which is carbon. So we need to put in both these phases to facilitate conduction as well as facilitate mechanical rigidity. So previously what we had was only the active material and electrolyte were making up the total volume. Now what we have is, once we add the third phase, we are sort of cutting off the excess on either side. And what that would do is, it will sort of shrink these windows, and it will not shrink the windows in a helpful way, it will rather shrink the windows in an opposite fashion, because it will cut off the part of active material which gives higher area. It will cut off the part of electrolyte that gives you lower resistance. So if you have 10% active material, this is sort of the window you're looking at. Now your 60% limit plus 30% and the rest is 10%. If you go at 20% carbon binder, and these numbers are by volume, all numbers are by volume, then you are making it even worse. If you go and add 30%, it's even worse. And you sort of see this gradual decline trend. And as you are going down and down, it means your electrolyte transport resistance is increasing. Now, there's just, if you had this new phase, there's an additional issue that comes out because these phases are now covering the surface of active particles. So you're going to be docked in terms of the active area that is available for reaction. Equivalently, these are not as, this will create more tortuous pore networks. And so you're going to increase your transport resistance, and which will make our life even worse. And if you go back to this time constant plot, this is how things will look like. When you have these composite porous electrodes, your now time constants for electrolyte transport become even larger. That means you're going to run into these limitations faster and faster. Now, what's the advantage of having this information? The advantage of this information is that now you can systematically tune your electrolyte for different applications. So let me illustrate that by an example. So for example, we start with this baseline recipe, and the way we go about it is, once we have the electrodes, we sort of know what the composition is. So we know the volume fraction of different phases. The information that we don't have is what's the actual area and what's the actual tortuosity. So what we do is we would use the appropriate porous electrode theory model to get a fit with the experimental data. So the dots are experimental data across various rates. And then from there, once we have this theoretical information, we can construct these resistance plots. It sort of tell us how much is the resistance from which of the transport processes at what different rates. Now, for this particular electrode, as it turned out, we were mostly limited by reaction. And if we were limited by reaction, we weren't limited by transport. What we could do is, now I can reduce my porosity even further. I can even reduce my carbon binder content because I'm not limited by conduction in the carbon binder phase. So I can sort of reduce both of them, get more active material and get more area, as well as get more energy. So as it turns out, after just two of such systematic changes in the design, you increase your energy density by about 12%. And it's across different rates. It's not just increasing at one rate. So having this information about what are the different time scales and what are the different forms of resistances help you do a systematic design where you carefully, surgically only modify the process that is most detrimental to you. Let me show another example. So the previous one was for a single electrode. Now, in this case, we have two electrodes as a full cell configuration. And what I'm showing you on this map are different candidate electrodes, so positive electrode and different negative electrodes. All of these candidate recipes are such that you always have the same amount of active material on cathode, which is 60%. And equivalently, you have the same amount of N to P ratio, which also fixes the amount of active material on cathode. So now the only thing you are varying with is you're changing the amount of carbon binder and you are changing the amount of porosity at each of the electrodes. And the colors that I'm showing you are sort of the capacity that you get normalized by the maximum theoretical capacity at 1C. You can see that increasing porosity and decreasing carbon binder helps you improve this capacity. And each of the electrodes have a different effect. Your negative electrode has a much stronger effect on improving the performance of this cell rather than making changes on the positive electrode. So this kind of going back and looking at what are the essential resistance spots lets you systematically change the things that are most hurtful. Now, in all this calculation, there is a source of variability. And the variability comes because this distribution of carbon binder phases at the interface is not unique. Depending on how you prepare, depending on your electrode fabrication conditions, this and that is going to change quite a bit. Thankfully, the part that is we are certain about is that it will contribute negatively, and it's going to have more and more detrimental effects if we let more and more carbon binder phase. Now, so it gives a general guideline of what to look for. And then if you have a specific data, then you can go back and construct those resistance maps for the particular electrode that you're preparing in your lab or in your company. And then you can go and do even more accurate design of these electrodes. So I posed this question at the beginning that given the electrode material, say I'm only going to work with nickel manganese cobalt oxide, say I'm only going to work with graphite on the negative electrode side, can I have a suitable geometrical arrangement? Now, first thing we would have to think of is what do we mean by best performance? And you would need to worry about these variabilities. So the concept that comes out of this is that we can now design with variabilities, and then we can do design that is targeted electrochemistry, which is the electrochemical performance of it. We can do design which is targeted at the heat generation of the electrodes, right? So think of just by making microstructural changes in your electrode, you can control the amount of heat your battery is going to generate, and you can get around quite a bit of external cooling requirements that you would have to put in. Another thing you can do is you can also design for degradation, because the processes that degrade these batteries over time, things like plating and SEI, they are fundamentally transport processes. So they would have an effect based on what your microstructure is, right? Now, let me pause a few minutes here and then get on to the inhomogeneous part.
Yes, you can. You have several questions in the chat. You can check the question section.
Okay. Okay. I think it would. Could you just read a few questions to me? I think that would be better. Okay. Oh yeah. I still don't see it.
We can read it.
Yeah.
So,
Yeah. Yeah. Please. Okay. So what happens is, and that's an interesting question because if you look at the literature, oftentimes you see quite a bit amount of carbon binder phases that people put in. Now, what turns out is you only need to put carbon binder phases up until you get to 1 to 2 Simon per meter conductivity. Once your dry electrode conductivity hits that value, beyond that, putting more carbon and binder phases isn't going to make any difference to your performance. And you can get to that value with much smaller amount of carbon binder than you would think. So can do electrodes that are to speak in more conventional parlance, can do electrodes like 95, 2.5, 2.5. So 95% active material, 2.5% carbon, 2.5% binder, and about 25% porosity. And as long as you're within 50 micron, 60 micron range, you wouldn't run into the conduction limitations from the electronic conduction. So the magic figure you need to look at is about 1 to 2 Simon per meter conductivity of the dry electrode. And the reason that figure comes out is because the ionic conductivity of the electrolyte is of the order of that value. So it's about 1 Simon per meter. So as long as you are conducting faster than the ions in the electrolyte, you are not going to run into the limitation from the carbon binder phase. Mm-hmm. Okay, okay. So now, as I said, it would change very much on whether your cells, what you're designing your cells for. So there are things like energy cells, there are things like power cells. If you 18650, typical electrode thickness you are going to run into is about 80 to 90 microns on both anode and cathode side. And the thickness in between would be fixed from the separator that you use. The typical separator thickness is about 20 micron. So you have to be a little bit careful about this because there are three things. Your total volume is now made up of active particle, carbon binder phase, and porosity. And at a time, you can change two of this. And the third will be set by itself. So the way I'm showing this plots is we are fixing the amount of active material, and then we are changing the carbon binder and porosity volumes. So if that's the case, then by increasing porosity and decreasing carbon binder, you would be able to get higher capacities. Similarly, if you fix porosity and now play with active material and carbon binder, then you would get a better capacity by going to higher active material packing, and you would only need a little bit of carbon binder to give the relevant electronic conduction that you need.
No, there is Mark Asutosh. There is one more question
Sure.
asked in the chat. Actually, in the chat, yes. How do you how do we predict the homogeneous distribution of carbon in low percentage? Question from Vasu.
That's an amazing question, and so we as a community we still don't have an exact answer to that. There are a couple of things that so sort of rule of thumbs are you need to dry your electrodes not too fast. If you dry your electrodes too fast, let me go to this. So if you dry your electrodes too fast, you would get something like this finger-like patterns. If you dry them slowly, you would get something like that. But something like this film temp patterns, which is on the left side of the figure. But that all will depend on how you are preparing these electrodes. The second source of variability that comes is because we are not completely adapted to imaging these phases. So we can see that in SEM or XRD, but what we really want to look at is the 3D distribution of things. And there we sort of run into two methods. We either do FIB SEM that can detect all the relevant phases, but it doesn't give the large enough volume so that you can make predictions at the electrode scale. And if you do tomography, you wouldn't be able to get the relevant contrast to image this material. So it's not an exact answer just because there are challenges on either side of things on how to get it. And we have to involve some trial and error in it to get to reasonable distribution. Okay. Right. So your pore size will affect. So as long as you have a unimodal distribution, right? So as long as you have all spherical particles which are same size, no matter those particles are of 5 micron or they are of 50 nanometers, your tortuosity value will be the same. And you can do the mathematics. The length scale just cancels out when you do the dimensional analysis. Now, pore size will start becoming relevant when you start with multiple distributions of this particle. So you start with something like a bimodal distribution or even something going beyond that. Now, in that case, now both the average size of the pore as well as what's now the distribution of pores would start becoming relevant. And in that situation now, your smaller pores would be more resistive to transport than your larger pores. But again, it goes back to because your pore network is being sort of defined by what your particle size distribution is. So as long as you're in a unimodal part or close to a monodispersed particle distribution, your tortuosity would come out the same as long as you have the same porosity, same volume fractions. Okay. Okay. There are two recent works from Paul Sharing's group that I'm aware of, where they are showing this. Wait, is it? Could you repeat the question again? I want to make sure I didn't miss it.
Yes, and also I make a comment. I mean, I read a comment from Jan Thomas saying, I think a UC X-ray tomography cannot give you a clear image of the carbon distribution. The voxels received will be too large. Yeah. Often it's very hard to determine CBD from pores.
Yeah, yeah. So it actually goes back to the articles I was mentioning from Paul Sharing. What happened, the way you can do it is you would have to do some trick with it, either do a fine resolution imaging using FIB SEM and then scale it up, or do other tricks with it. Another method was having an iron doped, so you dope your carbon binder with iron, and then you can, so the issue that came out was the contrast. You cannot detect the contrast. If you dope it with iron, it's a high Z material, and then you would be able to get the contrast to detect it. So there are ways around it. Now, the question that gets back to is that you're changing your system in each of these techniques. So what you're imaging is really what you want to image, or you're imaging something else just because you went around it, right? And those are really the open questions for the entire field right now.
You have another question. So a lot of questions says, how does intercalation kinetics influence these results?
So intercalation kinetics would directly relate to the area that you have available for reaction. And then so you more or less the only thing you can change for reaction kinetics is area, right? You can do other things for transport, like change the length or change the morphology, but with reaction, more or less the only thing you can do is area. So, and then there comes out to be the property of the active material and the electrolyte that you use. So it's a property of the interface, and you really can't do much about it. It is what it is. Okay. Yeah. Yeah. Okay. Right. Right. Thank you. Thank you. Those are wonderful questions. I really like those. Let me get to now the last part of it, which is now we're looking at the inhomogeneous porous electrodes, right? So what I showed before was assuming that the anti-electrodes were homogeneous, essentially assuming that whatever is the distribution in a small pocket of electrode is the same distribution throughout the electrode, right? Now, if I take an electrode, and this is a large enough electrode sample, and we had to get this from tomography, what you get is something like this. So the average active material volume fraction for this electrode was about 50%, but there was distribution, large distribution. So the lowest active material volume fraction was about 30, the highest was about 65. And correspondingly, what would happen is that the local distribution of carbon and binder would also be different. And now the third phase sort of sets itself. So it would then lead to an opposite distribution of electrolyte, right? And the reason carbon binder sort of doesn't spread uniformly throughout an inhomogeneous electrode is because the way this carbon binder phases attach to the interfaces during the drying process. So during that process, they would attach to the locations where there is more active area, more area between active particles and the solvent that you use for drying. And that is going to be more where you have more active material volume fraction. So that's why you would simultaneously have more amount of carbon binder phase wherever you have more active material volume fraction. So you see it's sort of positively correlated. And then the porosity would exhibit an opposite trend. So just to point out, so look at this data point. You have a 60% active material, but your corresponding porosity is about 15%, which is really, really terrible, right? And you can now sort of do these calculations locally and then go back to this time constant plot. And what you would end up with is that now you would have within the same electrode, you would have this distribution of time scales. So you would have a distribution of transport time scales. And sort of the challenge for next generation challenge is talking about extreme fast charging, which means you want to charge this in about at 6C charge, which would be less than equal to 10 minutes. And then what would happen is some of these locations would now have a more sluggish transport than you can handle. So even though macroscopically, if you just look at the electrode average porosity, it would look like, oh, you're not running into limitations, but this inhomogeneity would indirectly bring you back into this transport limitations when you work with inhomogeneous electrodes. And again, keep in mind, this time constant sort of scale with a square of thickness. So if you go from a 50 micron thickness to say 75 micron thickness, this time constants are going to double, little bit more than double actually, 2.25 times, right? So the actual challenge for XFC is simultaneously doing 60 charge on a thick electrode with higher active material packing, right? And minimizing the heat generation and minimizing the plating as much as possible. And I'll talk about it in a minute. So first thing, let us look at the intercalation signature of this when you have an inhomogeneous electrode. So I'm showing you that's the same distribution now. I'm showing you as a map, and this is the in-plane view of things. So electrode thickness is across through the plane, and you have spots which have low active material, you have spots which have high active material, and if you average over all the spots, you get to your macroscopic value of active material volume. Now, what this would lead to is, this leads to preferential intercalation. So some spots will get filled in first and would consistently keep getting filled in just because they have lower resistance. And it's sort of intuitive to see why. So the locations with low active material packing, they would have lower carbon binder. So they would have lesser coverage of the reactions. They would have higher porosities. They would have smaller tortuosities. So it would end up diverting all your current to those locations. And that's why those locations will keep getting filled in while other locations are sort of lagging, right? Now, let us look at the same thing, what happens to plating. So this is the reaction that happens on the negative electrode, which is the anode. And what I'm showing you here are how this front of plating, so it starts depositing from the separator. And then see so the initial distributions are sort of mapping the active material distribution that you see on the right. But as time passes by, you start seeing more and more different patterns. And this comes because the necessary driving force for this reaction comes from the intercalation, which is the primary reaction. So it sort of sets the voltages that are going to drive the second reaction, as well as it will also set the local availability of ions that would participate in this reaction. So that's why what you would end up with is that this plating inhomogeneity would be related to what your active material distribution is. Now, the video I showed on the previous slide was sort of having inhomogeneous negative electrode and a homogeneous positive electrode. If you keep the same inhomogeneity profile, but if you now make your positive electrode inhomogeneous, it's going to give rise to a different profile. If you make the positive electrode inhomogeneous, but now flip, so sort of you align the low porosity spots with high porosity spots, you are going to see a totally different plating profile. And often you look at the experimental data and you see that there are all these irregular plating profiles. It hardly ever plates uniformly at the surface. And it's partly because these inhomogeneities, which are aligned, partially aligned, or misaligned, give rise to these patterns, which on the face of it looks like random. Right? Now, again, with this, there is a source of variability as well, which is that these inhomogeneity profiles aren't unique. If you, even within the same electrode, if you image different sections, you are going to see a different pattern, right? And what it would give rise to is that if you look at the plating maps, the kind of maps I showed before, they would all look different and they would have signatures of what the local variation is, right? But there are still some solace in the fact that if you average over the entire electrode, things are still going to scale, right? The sort of the electrode average information is still valid, and that sort of scales with the inhomogeneity. So the amount of disparity between the highest active material packing and the lowest active material packing would sort of decide how extensive or how severe this plating is going to look like, right? So there are these variabilities, but that doesn't limit our life, because we have, once we put them into our understanding, they let us come up with reasonable ways to approaching these problems, right? So let me put this as a summary slide. And the key message I want you all to take away is that there are these time constants that we need to be aware of. And as we think of this next generation of design, we are going to be more and more limited by what happens at the interface, what happens in the pore phase, right? So we would run into sort of two different types of inhomogeneities. One would be the inhomogeneities you would see at the electrode electrolyte interface, and which is essentially because of the non-uniform distribution of carbon and binder. The second would be this aggregation of active particles, which give rise to this porosity gradients in the plane of the electrode, which would also give rise to a different kind of inhomogeneity, and in turn, a different kind of electrochemical, thermal, and chemical response. Now, thankfully, we over past couple of years, we have now coming up with better and better theoretical predictions that we can now design with these variabilities. And just have to be mindful of that. These variabilities come from sort of two things. One is that the fundamental way we make these electrodes, which is the drying phase, as well as the instrument that we use to detect this invariability, these variabilities are going to affect what we get out of it. Let me pause there and open the floor for any questions. Thank you.
Thank you very much, Aasutosh, for a nice presentation.
Thank you.
So I think there is a couple of questions. So there's one in the chat already. Maybe Marco, you can read it. Yes.
Right, right. uh, that's a fantastic question, and I wouldn't have an exact answer to that. Partly because the things change quite a bit with the solvent you use. Things change quite a bit with the active materials that you use, right? And then things will change if you use the same active material, same binder, uh, same solvent. Things would still change with the temperature that you use. Now, sort of the things that you would run into is if you use too much solvent, it's going to take larger time to dry your electrodes, and it leads to creation of these cracks once the electrodes get dried up. So that is that issue that you would run into, right? Second thing is the solvent itself isn't critically deciding where this binder phase gets attached. So if you think about the physics of the problem, what is happening is you initially have an interface of active material and solvent, and you are replacing that interface with now two interfaces. One is the interface between interface between carbon binder and active material, and another interface is between now this carbon binder and your solvent. So what you're going to run into is something like a nucleation problem, where depending on the surface energies of these interfaces, you're going to decide what kind of binder will form at the interface. And as soon as you enter into the realm where surface energies become dominant, now you're not going to be able to do much with changing the volume of things, because they're totally two different interactions, right? Keep on changing the volume, it wouldn't affect the surface interaction. So it's a difficult problem, and I would say there is a huge scope for understanding both on the theoretical side as well as careful experiments. Right, 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 right. That is on the list of questions I prepared. So good. So what is going to happen is now think about what you are doing when you prepare channels, right? You are now systematically introducing inhomogeneities. So it may decrease, so it may allow you to have more better transport through the channels, but now you have all these inhomogeneities essentially at the crevices of these channels where you have sudden inhomogeneity, you would give rise to the negative effects. Second thing you need to think of is how many channels are you going to drill, right? So if you drill channels, you are going to decrease the energy density of these electrodes. So then it becomes a question of whether you want to have a high energy density electrode or you want to have an electrode which has better transport but then doesn't store much. But I wouldn't say that my answer is final because quite a few things can change, right? Another sort of issue I foresee in designing those kind of electrodes is the manufacturability of things, right? Uh, then the ways I have seen the recent work, there's a amazing work coming out of Neil Das Gupta's group at University of Michigan, where they have developed this automated rig which sort of laser drills the holes, and then you can do it systematically. You can preset the pattern and everything. It does it quickly, right? Uh, Question would be, how soon will we be able to integrate that, if at all those electrodes do give a better XFC performance? Yeah.
Good.
Yeah.
So there is another question from Cedric.
Okay.
Yes, what do you know about the Maxwell, now Tesla, dry electrode coating process? Supposedly, it should allow for thicker electrodes, so higher energy density with higher power.
Okay. Uh, could you repeat the first half of it? I sort of missed that.
Mark, you can put it in a live answer, then you can show in the screen. Yes. Do you see the question there?
No.
Okay.
No.
So what do you know about the Maxwell, now Tesla, dry electrode coating process?
Okay.
Supposedly, it should allow for thicker electrodes, so higher energy density with higher power.
Okay. I'm not familiar with that particular work. Let me check that up and then give you an answer. Do shoot me an email and I would love to talk about that.
Okay. So yes, I think yes, I know this guy Cedric, so I think we can drop you his email, right?
Perfect. Perfect.
Yes.
Thank you. Thank you.
Thanks.
Are there other questions? Okay. Uh, give give me a minute. I wanna show something. Yeah. Yeah. So let me leave you guys with sort of a question, right? So when we do mathematical modeling, we think in terms of functions, right? And the typical functions that would be mapping a scalar to scalar, something like the open circuit potential being a function of local concentration of lithium, or it would be a vector to vector mapping where it would be flux of lithium, which is proportional to the gradient of concentration, which is a vector itself. Or we would be mapping a vector to a scalar, something like dot product of current and volt potential gradient gives us heat generation, right? Now, if you think of tortuosity, it's an unusual function because tortuosity, if you the way you interpret it is either a vector or a second order tensor when you run into these inhomogeneous anisotropic electrodes. And it sounds a very unusual mapping because you are mapping a scalar to a second order tensor or a vector, right? Now, the reason this is interesting is because we might be missing some physics here. And if we are missing a physics, then there is an opportunity for innovation, right? Some of my early thoughts we published recently, and I would really love to talk to anyone who want to think about this, because this seems intriguing to me. Okay. That's all I had to say. Thank you.
Thank you very much, Aasutosh. Very nice conceptual things actually to end this first day of the webinar series. Thanks a lot for a very nice talk and all the answers. And so we are at the end of this first day. Yeah. So we would like with Mark to acknowledge everyone. So all the speakers, well, Ivano, you, Aasutosh, Theo, Lombardo,